I'm Mr. Kangas, and today we're going to take a look at Chapter 11, Section 5, Surface Area of a Pyramid. Now, surface area of a pyramid is much easier than surface area of a cone to explain. Just like with the cone, there are two essential pieces that you are looking to identify the area of. You're going to try to find the area of the base and the lateral area, just like with the cone. Same two pieces. However, finding the lateral area of a pyramid is a much simpler process to explain. So this video should not be as long as the cone video. Now, the key thing to understand about pyramids is they have a lot in common with prisms. Their bases can be any polygon in the world. So their bases can be any 2D polygon, whether that be a square, triangle, or even an octagon. Okay? Any 2D polygon can represent the base of a pyramid. And from the base, okay, the vertices of the base, okay, will rise up and meet at a singular point, and that's what creates a pyramid. Okay? The difference between a pyramid and a prism is in a prism, the vertices would rise up to meet another vertice opposite to itself. So it would just go straight up. It would go in a perpendicular line straight up and meet another vertice up here. Whereas in a pyramid, all of my vertices rise to a central point that actually hovers right above the midpoint or the center point of my base. But just like the prisms, the bases can change, and they can be any variety of shapes, okay, in a pyramid. So you have all kinds of different pyramids. We have triangular pyramids, we have rectangular pyramids, and we have octagonal pyramids, we have hexagonal pyramids, anything and everything. So the first part of the surface area formula is this big B, which, as we discussed in previous videos, represents area of the base. Now, how you find the area of the base is going to change based on what shape is in the base. And I will have a video on finding the area of bases that have more sides than 4, because it's basically doing pentagon and up. The process for finding the area of pentagons, hexagons, octagons, septagons, etc., is the same for every shape that is more than 4 sides. So that's part one. That's pretty simple to understand. You're finding the area of the base because the base represents one of your surfaces. The next part of the formula represents lateral area of the pyramid. So this small little snippet here in this formula will find you the lateral area. That includes every single surface in the lateral area. Okay? Whether you have 8 surfaces or 3 surfaces, this right here will find the area of all these surfaces. What you're going to notice is no matter what kind of pyramid you have, the lateral area is always composed of triangles. Triangles. And more triangles. Always, always, always. Because each side of the base, okay, only has 2 vertices because they're made of straight lines, and those 2 vertices rise to a central point. Whereas with a prism, the lateral area was made of rectangles because my vertices were both rising straight up to an opposite point. And so you had 4 vertices, which would create a rectangle. In this case, we only have 3 vertices per side because we have the 2 from the base and then the central point at the top. 2 from the base, central point at the top. 2 from the base, central point at the top. 2 from the base, central point at the top, etc. So, how does this find me all of this? That's a good question. Okay? First things first, you need to understand what the different pieces represent. L represents slant height. So the distance from the top down to the very bottom. So these little creases here that you see, or these lines that you see going from the bottom all the way up to the top, those are all representative of slant height. Okay? P represents the perimeter of my base. It represents this whole distance. Now, if you remember correctly, back in chapter 10, we talked about area of a triangle. This should look kind of familiar to you because it looks kind of like the area formula for a triangle, which is 1/2 base times height. Okay? Now, with a triangle, you always need to do 1/2 base times height. And since the lateral area is composed entirely of triangles, it makes sense that we would want to manipulate the triangle formula to come up with the lateral area. Basically, what's going on here in this octagonal pyramid, I have 8 triangles I need to find the area of. Here, I have 3 triangles in this triangular pyramid that I have to find the area of. And in this rectangular pyramid, I have 4 triangles in the lateral area that I need to find the area of. So how does this do all that? Well, let's start with the rectangular pyramid. Okay? Let's pretend for a moment that each base of the 4 triangles is different. Let's say I had a base of 2, 3, 4, and 5. Okay, so we'll say that this side is 2, we'll say this side is 3, this side is 4, and this side is 5. Now, obviously, these 4 sides look the same. This is just hypothetical. Let's assume that this side is 2 inches long, this side is 3, this is 4, and this is 5. So I'm talking about the base, the distance from one vertex to the next, so that straight line there. Because remember, to find the area of this triangle here, I would have to do 1/2 times height times base. So in other words, I'd have to do 1/2 times height times 5, plus 1/2 times height times 2, okay, etc., etc. Now let's pretend for a moment, one thing that is going to be the same about all these triangles, no matter what kind of pyramid you have, okay, one thing that's always true, every triangle in the lateral area has the same slant height, or the same height. Okay, each one of these triangles has the same height. Now, we have to represent height of the triangle with slant height. Okay, because remember, the distance from the top down to the bottom, okay, represents slant height if I'm traveling along the pyramid, which would also represent the height of my actual triangle on the lateral surface. Okay? So the height of this triangle is actually represented by slant height, not by regular height. Regular height would be going right from the bottom straight up like this. And that's not going to represent the height of this triangle. I actually have to be on the triangle to find the real height. Okay? So slant height represents the height of my triangle, and every one of these triangles has the same slant height because the distance from the base to the top does not change. Does not matter which side I'm talking about, because all of these vertices are rising up to meet the same point. Okay, so that height's not going to change because they're all rising up to meet the same point. This point's not going to be down here on this side, but up here on this side. That would make sense. Okay, so the slant height for all of these triangles is the same. And so right now I have the height of these triangles represented by slant height, and I have all the bases of these triangles. So I have 4 triangles I have to find the area of to get my slant height. I have 4 triangles I have to find the area of to get the surface area. If I want to get the surface area of the lateral surfaces, I need to find the area of all 4 triangles. And so here are the bases that I wrote down. Okay, I made the bases up. Okay. L represents the slant height, which is actually the height of the triangles. Okay. And then 1/2 finishes off the formula. Okay, so I have 1/2 times slant height times the base. So in other words, area of the triangle with base of 5, area of the triangle with base of 4, area of the triangle with base of 3, area of the triangle with base of 2. Okay, So if I take all these areas and add them up, I will have the lateral area of my pyramid. So that seems like a lot of work there. Okay, let's pretend for a moment that slant height is equal to 10. Remember, the slant height is the same for all the triangles always. Then what I would do first is 1/2 times 10 for all of them, because it's going to be the same on all of them anyway. So that'll help simplify things. So I'd have 5 times 2, 5 times 3, 5 times 4, and 5 times 5. Okay? At this point, it's just a matter of finishing off the multiplication. 5 times 2 is 10, 5 times 3 is 15, 5 times 4 is 20, and 5 times 5 is 25. So now I have the area of each individual triangle. And now I just need to add that up, and I will have my lateral area. So my lateral area is equivalent to 70 inches squared. Okay? That's a lot of work to find the area of these 4 surfaces. Now imagine doing all that work to find the area of 8 sides in an octagonal pyramid. Or let's say I had a 100-gon pyramid. Okay? Then you'd be finding the area of 100 triangles. And that could take some time. I don't want to do that. There's a much simpler way to do that. If we take a look at this second step here, because what you noticed was the slant height was the same for all of them, and they all had 1/2, because area of a triangle is 1/2 height times the base, or 1/2 base times height. Doesn't matter what order you do it in, but this is 1/2 height times base, and the height was the same for all of them, as was the 1/2. So I got 5, 5, 5, and 5. So that was in common with every single triangle. What was different about every triangle was their base. Their bases were different sizes. Okay? But I did have a common theme, which was that 5. So if we take a look here, this should remind us of the distributive property. Because the distributive property is taking one number and multiplying it by many numbers. Okay? Remember distributive property. If I have the 3 on the outside, and I have a 5 plus 7 plus 8 inside, I'm doing 3 times 5, 3 times 7, 3 times 8. So I'm multiplying that 3 by many numbers. I'm multiplying 5 by many numbers. So instead of doing all this work and finding each triangle individually, I could just take the 1/2 times 10 and multiply it by the perimeter of the base, which would be adding up all these sides here. So 2 plus 3 plus 4 plus 5. And if I were to reduce, or if I were to simplify that, okay, all these added up are 11. Now I can multiply the 1/2 times 10, and I can get 5. So at this point, I have a choice. I could do 5 times 11 and get 55,